All right, picking up where we left off. So if we want to optimize with gradient descent, well, ultimately what we're trying to do is find the bottom of our empirical risk surface. So this is the empirical risk as a function of beta 1 and beta 2, where beta 1 is our intercept and beta 2 is the weight of the radius. And so we can see that if we were to try and, if we started here in gradient descent, we would ultimately want to go down, 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 and the minimum is somewhere along this ridge, though it's hard to tell from this figure. Okay, but that's what our goal would be. And that's kind of what we were doing before when we were doing brute force. Okay, oops. So in order to minimize the surface with using gradient descent, we are going to need to find the gradient of this function. Okay. So what is the gradient of the function above? Well, it's given by this expression. Okay, and I'll talk about where this came from in a bit. But this expression here, it is the gradient of my risk, that is of my cross entropy loss. So if I plug in minus 14.5, I get that the gradient is minus 0.35 minus 6.1. And so that tells us, the way gradient descent does, that what we really need to do is we should sharply increase this right parameter, and we should increase this one somewhat. That's what this expression wants to tell us. It says that right now, where we are, so this is minus 14.5. Let's go look at it on this chart. So at minus 14.5, right around here, it's quite steep in the beta 2 direction, and that's what the gradient here is telling us. Okay. Now, where did this function come from? You might ask yourself. It seems simple. There's not a lot of code to it. There's actually a lot of work. I would estimate that if I just sat you down and I said, come up with a function that returns the risk gradient, the average student in this class, I would bet this would take several hours. Okay, this piece of code would take several hours to come up with. Okay, now that may seem surprising, but it's actually pretty challenging. So just to give you a flavor for where it comes from, because I don't want to go through the whole derivation because it's very boring, we start from the original thing we're trying to do. That is, this is our empirical risk, and then we apply the gradient operator to both sides. Okay. Now, how do I do that? Well, I need to substitute in my cross entropy loss on this side and to do a little bit of calculus and then a ton of algebra. And what you'll find is you end up with this expression below. So this expression, if you apply the gradient, you get this. And you might look at this and see, okay, well, it makes some sense. Like, it's not so surprising that if I compute the gradient, I get something that looks like this. But if you actually look at the full derivation, there's actually quite a lot to it. So if we go up here, this is all the algebra at the very end that shows you, if you want, I really don't want to go through this, but it's there if you're curious, that this expression here is the empirical risk written a different way. And then when the gradient operator is applied to it, you end up with this expression. Okay. So why am I not walking through this? It just feels like not important to our course. It's just a bit of algebra that we don't really care about. Okay. Now, if you're curious, you can sit down with it and get there. Okay, so once you have this expression, then what? Well, then we can implement it. So this expression implemented in a straightforward way looks something like this. So n is the number of rows in my design matrix. We need to total up all of my cross entropy loss. And we'll have a for loop where we go through each observation, as this suggests. We take the y, subtract out sigma, the x, the dot product of x beta, and then multiply this whole thing by x, as it says up here. Then we'll return minus 1 over n times this total cross entropy loss, and we end up with the gradient. Okay. Now there's some bad news. This code is very slow, and it's because it uses for loops. Now, if you ever go and think carefully about numerical optimization, there's something known as vectorized code, where you can write code in a smarter way that will take advantage of your libraries and how they're implemented to be fast. This is well beyond the scope of our class, but bottom line, this function here is the equivalent of this function at the bottom. This is the version that uses matrix multiplication. I'd say getting from this code to this code is pretty challenging. So I just wanted to give you a flavor for where this risk gradient comes from. But really, what I want you to understand is what this means. I give it a current beta, it gives me a slope. And these slopes correspond to how steep this function is at that particular point. And the exact expression I used here, well, you know, it took a lot of work to derive. Okay. Now, just in case you want to see the gradient itself, one way that this is often done is something known as a quiver plot. And this quiver plot shows you the gradient at any given point. So if we're in this position, the gradient is very sharply pointing up. And so gradient descent, what we need to do is go in the opposite direction of the gradient. So you can think that what gradient descent does is, in any given position, it goes the opposite direction of the arrow, trying to get down to the bottom of the surface. Okay. All right. So now that we have a gradient function that we can use, we need to apply gradient descent. All right. How do we do that? Well, the good news is that you have actually already implemented gradient descent on homework 7. You've seen it. You know exactly pretty much how it works. The bad news is I had to add one more little feature in order for it to work numerically. Okay, so this, I'm just going to walk through this code very quickly because it's almost exactly like what you did in homework 7. We start from a starting guess. We then, for each iteration, compute the gradient. We then pick the next beta by subtracting the gradient multiplied by a learning rate. Now you'll notice that the learning rate is decaying, similar to what you did in homework 7. But there's another thing that we're doing to the gradient called clipping. What does clipping do? Well, let me show you an example. So we'll go back up here. Okay, here is the risk gradient. No. Laptop. I know I'm recording, but it shouldn't be this slow. Okay, let's make a new cell. Wow, it's mind-numbing. All right, NP clip. Oh no, that's too much stuff. Okay, this. Okay, NP clip -1, 1. What this does, if either of the components of the gradient is outside of the range you specify, it clips it. It sets it equal to that value. This is too small, so we make this say -1. Okay. Why am I doing that? Well, it basically says if the gradient happens to be very large in some direction, we don't want to overshoot to the other side. So if we clip the gradient, it avoids you from jumping too far. And in this case, I picked some arbitrary value. It's a lot of thinking and guess and check when it comes to numerical optimization. In my case, I mostly did guess and check and ended up with deciding that a clip of 1 was about what I wanted. Okay. So this gradient descent function, if we run it, will give us our optimal beta. So that is, if I define a function called logistic regression, you give it an x and a y, we'll make a starting guess, and we'll use gradient descent, and then we'll return you your optimal beta. So if I run this function, which I won't do now because it'll be slow, it'll take around 13 seconds and generate an output something like this. So when it's done, the gradient's norm, that is the sum of its components squared, will be pretty small. And then the optimal beta that we end up with, well, it's pretty close to what we were guessing. I said -14, 1. It came up with this slightly different number. Okay. If we look at the risk gradient at this point, we can see that, I'm going to run it. No, okay, actually, no, it's fine. Okay, so we run the risk gradient. We see that it's quite small. Yeah, all right. And so what that means is, as you expect, at the optimal value for beta, we expect that the gradient should be around 0. Okay. Now, if we plot this model of this beta we came up with, we see that it's pretty good, right? It looks very similar to what we had before. And if we look at the average cross entropy loss, well, we get 0.29998. Okay, so that's what it came up with. Now, to end this specific section of the video, I want to show you that what we've just done is essentially just the same as the incredibly powerful scikit-learn library. So if I create a logistic regression model, and we say, please do not fit an intercept because I've already created my own bias term, and then I say, don't do any regularization, I'll come back to that at the very end of this lecture, fit a model, and then look for its coefficient, it will very speedily come up with values that are not very far off from ours. Ours were negative 14.13, 0.957, it came up with negative 14.9, 1.0106. Which one's better? Well, the scikit-learn one is slightly better if we look at it. This is 0.29966. Ours was 0.29998, but we were pretty close. If we plot their model, looks almost exactly like ours. Okay, so here, what this tells us is our model is quite similar. What we've learned in this course really does get us about the same result as scikit-learn. And so that's pretty powerful. Yes, we did do some fancy stuff that you would have a hard time doing, specifically coming up with this risk gradient. But the basic principle is there. I think you could derive this, it would just take you a long time. All right, so great. We've done gradient descent. We've seen that it really does work for doing logistic regression. And I really hope that that all made a lot of sense to you. I know I went through it fairly quickly, to me, but the hope is that with all the knowledge you built throughout the class, you were able to follow that narrative. And if not, well, get some more practice, maybe come watch this again. And so what we'll go on from here is we'll start looking at how we can do even better using regularization and evaluate the power of our classifier. Okay, that's the most important punchline, I think, of what we're going to do. But then we'll cover some of the other stuff we've talked about today, like linear separability and regularization in the rest of this demo.